the Sydney CPPC seminar. Today's speaker is Bhupal Dev from Washington University in St. Louis. So Bhupal did his PhD with Ravi Mohapatra at the University of Maryland. And after that, he moved to Europe for postdocs at Manchester University and then Heidelberg at the Max Planck Institute. And since 2016, he has a faculty position at the Washington University in St. Louis and is now associate professor, if I'm correct. And yeah, so he will be telling us about multi-messenger probes of the nature of neutrino mass. Yeah, so please, Bhupal.
Thank you, Michael, and good morning to everyone. For me, it's going to be evening. And I really thank Michael for the invitation and for the opportunity to present our recent work in this seminar. I'm sorry, my throat is a bit sore, so I might be pausing in between to cough a little bit. I apologize for that in advance. So this work we did in collaboration with an outstanding graduate student at Harvard, Kyra Carloni, her supervisor, Carlos Arguelles, who is part of the ISCIP collaboration. Then Ivan Martinez Soler, who was a postdoc with Carlos at Harvard. Now he's a faculty at Durham. Then Kaladi Babu is a professor at Oklahoma State. This is the reference. The paper was out last year, December. Still fighting with the referee. And then there's a follow-up work that I've been doing with Pasquale Di Bari from Southampton, his postdoc, Rishabh Roshan, and Ivan. So this talk will basically be two parts. The first part, I'll talk about the ice cube, and the second part, I'll talk about some excess radio background. Okay, so before I begin, let me motivate why multi-messenger neutrino is a good probe of physics beyond the standard model. So here is a plot which shows the neutrino energy on the x-axis, and you can forget about the y-axis. It doesn't really matter for our for the discussion here. So we have, as you can see, we have a huge range of the energies of the neutrinos, starting from the relic neutrinos, sub-eV, all the way to the cosmic neutrinos, the galactic and extragalactic neutrinos around 10⁻16 to 18 eV. So like about 20 orders of magnitude we have for all these different neutrino sources. And they give us incredible amount of information. For example, we know that the solar and atmospheric neutrinos were used to discover the neutrino oscillations, which means that we have a non-zero mass for the neutrinos. And now there is this suite of experiments in all these different energy ranges, trying to probe the neutrinos across all these different energies. So what I'll be focusing on in today's talk is the rightmost part of this this picture, where we are looking at the high energy neutrinos, extraterrestrial neutrinos, mostly coming from extragalactic sources. And there are a bunch of experiments which are trying to find the properties of these neutrinos, but we'll be using them to study beyond the standard model physics, and I'll explain how we can do that. Okay. So as I mentioned, we know that the neutrinos oscillate between 3 different flavors, and that means that at least 2 of the masses must be non-zero. And this is already physics beyond the standard model, because there is no way in the standard model we can accommodate the mass of the neutrinos. Now, if you look at the spectrum of the masses, we don't know, of course, what's the absolute mass scale, but since we know the mass square differences, and then there's this limit on the sum of the neutrinos from cosmology, we know for sure the neutrinos have to be below the electron volt scale. And this is very different from what we have for the rest of the particles in the standard model. In particular, for the charged fermions, their masses are clustered around MeV to GeV, 200 GeV scale. So the neutrinos are much, much lighter than the other charged fermions. And the question is why? So perhaps this gives us some hint that there is some other mechanism beyond the standard Higgs mechanism that gives mass to all the fermions in the standard model. So perhaps neutrinos get mass from some other mechanism. And that's one of the fundamental questions. What's the nature of the neutrino mass? And it's interesting that the neutrinos are the only fermions in the standard model which are charge neutral, electrically neutral. So in addition to having a Dirac mass, like the charged fermions, they can also have a Majorana mass, which means that they can be their own antiparticles. This is possible only for neutrinos in the standard model. or there could be something in between. And that's something that I'll discuss. So here I must emphasize that this is an experimental question. Okay, so what's the nature of the neutrino mass? Of course, the theorists can have their own prejudice. They can some people might have their own favorite models for whether it's Majorana particle, or some people might think that it's a Dirac particle. But eventually it's experiments which can really tell us what's the answer, right? So we need to devise experimental probes to test the nature of the neutrino mass. Now, the best known experiment that can test the nature of the neutrino mass is the neutrinoless double beta decay. The picture is shown here. I'm sure you all are familiar with this. We all know the beta decay. So we have neutron going to proton plus electron anti-neutrino. You can have two of them. And this process has been measured in the labs. The lifetime is incredibly long, like 10 to 21 years. But now if the neutrinos are Majorana particles, then you can close these neutrino lines, and then you only emit 2 electrons without the neutrinos. That's why it's called neutrinoless double beta decay. Now this process has not been measured. There are only lower limits on the lifetime of this process, which is around 10 to 25 to 26 years. There's a theorem called the black box theorem, or the sector value theorem, which tells us that if this process is ever observed in nature, then neutrinos must be Majorana particles. Now, irrespective of what is the mechanism for the generation of the Majorana mass, but they must be Majorana particles, okay? Because this process is clearly lepton number evaluating. Now, this is the picture which shows the experimental prospects of the neutrinoless double beta decay in the next, 10 to 20 years. So the gray shaded region here, that's the exclusion from current experiments like Amlanden and Gerda. It excludes this parameter called effective neutrino mass around 0.1 eV. And the future experiments, the next generation ton scale experiments like NEXO or Legend 1000, they have the sensitivity to go down to close to about 0.01 eV. And these two bands that you see, the blue band and the green band over here, so they are the predictions for the canonical light neutrino contribution to double beta decay through this particular diagram that's shown here. If the neutrino is in inverted order, then there is this strict lower limit that we have. M beta beta should be larger than about 0.01 or 2 eV. And this can be reached by the next generation experiments. But if the if the neutrino mass is inverted order, then there's a hope that we might be able to get a positive signal of this process in the next generation experiments. However, if the mass ordering is normal, and there is some hints from the most recent oscillation data that the mass ordering is in fact normal. Again, that's not statistically significant yet, but there's a 2 sigma preference for normal ordering. In that case, we may not be able to get any signal in the double beta decay experiments, right? That's what is shown over here. And there are independent limits coming from the right on the mass of the lightest neutrino. Planck gives a bound on the sum of the neutrino masses that is currently about 0.1 eV. And then Catherine is directly measuring the electron neutrino mass, absolute mass, and the current bound is about 0.2 eV. So we are basically closing in from both right and from the top. But if the neutrino mass is normal order, then there might be a possibility that we won't have any signal in the next generation experiment. So then the question is, how do we then know if the neutrino is Majorana or Dirac? That's the question that we're trying to address here. Okay. So before we go on to the other experimental tests, first let me step back and discuss what we know from theory so far. We know that the neutrinos are massless in the standard model, and that's because of various reasons. First is that there are no right-handed partners to write down the Dirac mass term like you do for the charged fermions. And then the second reason is that you cannot even write a Majorana mass term in the standard model for the neutrinos because the neutrinos are part of the SU2 doublet. So if you write a Majorana mass term, that behaves like that's the triplet term, so it breaks the SU2 gauge invariance. So you cannot write this in the standard model. And then you have non-perturbative effects like the spiralons, electroic spiralons. They do break lepton number. They actually break B plus L, but they still preserve the B minus L. So they also cannot generate neutrino mass at any order. And finally, there are gravitational effects. You could have some theory of quantum gravity, and then they could induce some mass term for the neutrinos. But naively, these effects will be roughly order of electroweak scale square divided by the Planck mass, which is about 10 to the minus 5 eV. Now, this is well below what we know from atmospheric mass splitting, that the neutrino mass has to be about, the mass splitting has to be about 10 to the minus 3 eV square. So you cannot explain that using even gravitational effect. So as you can see here, so there is no way in the standard model that we can have mass of the neutrinos. Now, the simplest possible solution is to just add a standard model singlet Dirac partner, a right-handed neutrino. So you can write the Dirac mass term and then just say that, okay, because the mass is known to be EV scale, sub-EV scale, the Ikawa coupling is about 10 to the minus 12, something like that. This is perfectly fine. There is nothing wrong with that. But if you just have that and nothing else, then that situation is really boring because you don't have any signature in the experiments. But there is a stronger reason why that cannot be the whole picture. As soon as you write down this Dirac partner, the right-handed neutrino, then because this is standard model singlet, now there is nothing that prevents it getting a Majorana mass, right? So it also allows for this Majorana mass term for the right-handed sector. And then you can write the full neutrino mass matrix, which is now a 6x6 matrix for the 3 flavors of active and 3 flavors of steriles. And you get this mass matrix, which is typically known as the seesaw mass matrix. Now here there are 3 possibilities that you can have for the masses. So if this MR, the right-handed neutrino mass, the Majorana mass is exactly 0, then there's an exact lepton number symmetry in the theory, just like in the standard model, and the neutrinos are exactly Dirac particles. Okay. And if this Majorana term is non-zero, then the neutrinos are Majorana particles. Now there is an intermediate stage, what I call intermediate, because if the Majorana mass term is much smaller than the Dirac mass term in this matrix, then the neutrinos become what I call pseudo-Dirac. That means they have a very small active sterile mass splitting. Now this is the scenario that I'm going to focus. I'm going to show you how we can prove these pseudo-Dirac neutrinos using the astrophysical neutrinos. Excuse me. But you might wonder, okay, why this is a natural scenario? Why the Majorana mass term has to be smaller than the Dirac mass term? And in fact, in the original seesaw mechanism, the Majorana mass term is actually much larger than the Dirac mass term. And that comes from the motivation from the grand unified theories, where this Majorana mass term sits at the gut scale 10 to 14 GeV, and you generate this Dirac, and the Dirac mass term is proportional to like the top quark mass in the S of 10. And then we have the natural scenario where the Dirac mass is much smaller than the Majorana mass term, and that is that's the celebrated seesaw mechanism, where the light neutrino mass then becomes like the Dirac mass square divided by the Majorana mass, right? But it is logically possible to also have another alternative where the Majorana mass is much smaller than the Dirac mass. Okay, and in fact, this was discussed just right after the seesaw mechanism was proposed. In 1981, Wolfenstein was the first one to discuss this, but he only did it in the context of active neutrinos, and then Petkov generalized that to the sterile neutrinos, and there are a series of papers after that which discuss this possibility, but it's not as popular as the seesaw picture. Okay, so now let me discuss a little bit about the models of pseudo-Dirac neutrinos. The idea is very simple. A good starting point would be to have just a Dirac neutrino mass model. And the right-handed neutrino Majorana mass is exactly 0 at the renormalizable level. And this is, for example, in the Dirac seesaw scenarios. And this has a global lepton number symmetry. Now, we know that in any global symmetry will be eventually broken by the quantum gravity corrections. And then you'll generate a small Majorana mass term. It will induce a small Majorana mass term. Okay. And you can naturally realize this, for example, in the mirror models. I'm not going into the details of these models, but for example, in the mirror model, you can have a Weinberg operator, you can have a dimension pipe operator, which will induce a small diagonal, the neutrino mass entries. And in this scenario, the neutrinos will be pseudo-Dirac. There will be a small splitting between the active and the sterile. Now you can actually calculate what the mass splitting here. As I said, it's just B squared over M Planck once you break the electric symmetry here. And So you can find what's the delta m square. It turns out to be about 10 to the minus 6 eV square if you take the active mass to be equal to the atmospheric mass as maximum mass. And in this case, you'll also get maximal mixing between the active and sterile, which is simply given by 2 times mass of active divided by the mass splitting. Now, this is a simple model for the pseudo-Dirac neutrino. The question is this okay? Are there any constraints? Well, it turns out this is actually excluded. And this is excluded doubly. First, it's excluded by the BBN data, which tells you that if you have such a sterile neutrino with maximal mixing with active neutrinos, then you spoil the BBN unless the mass square splitting is extremely small. And extremely small, I mean less than 10 to the minus 8 eV square or so. There's very old work by Beridoldo which showed that. And after that, there are also a couple of other works which kind of confirm this particular limit. But then there is a stronger limit which comes from solar neutrinos. And the idea here is that if you have a pseudo-Dirac neutrinos, then you'll have energy-dependent oscillations in the solar neutrino spectrum. And the solar neutrino spectrum has been measured very precisely now by different experiments like Borexino, Camland, and so on. And recently, there is a reanalysis of all this data, and they got a bound of delta m square less than about 10 to the minus 11 eV square. So in the model that I just told you, the delta m square is 10 to the minus 6. So this is way inside the exclusion region of the solar neutrino data. So the question is there a realistic model of pseudo-Dirac neutrinos? And the answer turns out to be yes. Otherwise, I won't be giving this talk. So one of the possibilities is to have, instead of having a global lepton number symmetry, you gauge the B minus L. And that is protected by, so you do not have the quantum gravity corrections for this model at the dimension 5 level, but you'll have at the dimension 6 level, and that makes this model work. So we can introduce like a singlet scalar which carries 2 units of B minus L, and then the lowest order quantum gravity corrections will be dimension 6. And then you have the leading contribution to the mass splitting, which comes from V square B minus L breaking divided by the Planck mass square. And you can plug in some numbers and see that for a typical VBL scale, if you take it to be the gut scale, then you get a delta m square 10 to the minus 12 VB square, which is just below the solar neutrino constraint. And if you take the VBL to be the smallest possible value, which is about 10 TeV, you cannot make it lower because of collider constraints. But if it's 10 TeV, then you get a delta m square, which is much smaller, like minus 22 eV square. So as you can see, you can generate a range of these delta m square values for the active sterile mass splitting. And this is obviously consistent with the solar data. And there are other examples of the pseudo-Dirac models. You can, for example, you can have a left-right scenario where you can also have a delta m square which depends not only just on the B minus L breaking scale, it also depends on the SU2 right breaking scale. So the bottom line is that any model of Dirac neutrinos with Planck suppressed operator would predict a pseudo-Dirac neutrino. Now, if you have just the Dirac neutrinos, then there's a concrete prediction for the delta n effective, which is about 0.14. And this is testable in the next generation CMB experiments like CMBS4. But if it's pseudo-Dirac, then is there any way you can distinguish it from the Dirac neutrino, right? So it looks like a difficult question. In particular, can we really have access to this tiny delta m square values? So if delta m square is 0, then we know it's a Dirac neutrino. And if delta m square large, then we have the Majorana neutrino. Now, in the intermediate range, if you have a small delta m square, is there any way we can test this in the experiments? Now, so perhaps the best way to test it would be to use the oscillation effect, but the oscillation effects are suppressed for a small delta m square because the oscillation effects go like delta m square L over E, and unless this quantity is of order 1, you do not have any oscillation effect. Okay, so you need to find the length. L is the length of oscillation in the baseline length, and E is the energy of the neutrino. So you have to find suitable L and E, which will give you delta m square L over E of order 1. And this turns out to be a challenge if you have very small delta m square. So this is shown in this plot here. So on the excuse me. On the x-axis, we have the length, the oscillation length in meters. On the y-axis, we have the energy of the neutrino in MeV. And all these different lines, they are the contours for this delta M square, for different values of delta M square that you can probe using this combination of L and E. Okay. Just for reference, the solar atmospheric, so that is shown by the red lines here. That's 10⁻³ and -5 eV square. And so yeah, if you have active sterile mixing, which active sterile splitting, which is of this order, then you can probe them by using the usual either the atmospheric mixing experiments or accelerator reactor experiments. But now if you have delta M square smaller, then the only way to probe them is to go to astrophysical baselines. Okay, so here's the sun, so the solar baseline. So if you have delta M square 10⁻11 eV square, then you can probe them using the solar neutrinos. And that's precisely the bound that I just mentioned before, 10⁻11 eV square. Because if you have mass splitting less than that, then the solar neutrinos are not enough to probe it. You have to go to longer baselines. And the only other long baselines that we have is either you find a supernova or you go to some astrophysical neutrinos. These are the only possibilities, right? Now for supernovae, which is here, this is the galactic supernova. So here you can probe delta M square down to about 10⁻20 eV square. Okay, extremely small delta M square. There's another possibility you can do. You can have it. This is the diffuse supernova neutrino flux coming from all over the universe, but this has not been measured yet. Though we believe it exists, and hopefully it will be measured in the future neutrino experiments, the big experiments like Dune and Hyper-K. But for the time being, we don't have it, so we just have to live with the supernova, and we have only one supernova, galactic supernova neutrino events detected, which is the SN 1987A. So I'll show you some results from that. But then another interesting possibility is to go to the high energies where we have the astrophysical neutrinos, which is shown up here, and they can also probe this mass splitting range 10⁻15 to -20 eV square. Okay, so that's the main focus of this talk. Okay, so before I go to the high energy neutrinos, let me first talk about the supernova neutrino constraints. So what will happen is that if you have this small splitting and maximal mixing, then you can have oscillation probability, active to active transition. It will be modified instead of just becoming half, which is true naively speaking. But then you'll have another term, which is an oscillation part. If your oscillation length is of the right order, then you get this oscillation pattern. And it turns out the oscillation length for EV scale, for MEV scale neutrino energy and delta M square about 10⁻19 EV square turns out to be 20 kiloparsec. This is the typical size, the typical distance scale to a galactic supernova. And there is also the coherence length here, which needs to be larger than the oscillation length. Otherwise, the neutrinos will decohere. But it turns out the coherence length is about 100 kiloparsec, which is larger than the oscillation length here. So this is fine. Okay, so once you do that, then what do you see? Well, here is a picture of the spectrum. This is the energy of the neutrino, and then this is the flux, well, E square times the flux. And if you have standard oscillations without any pseudo-Dirac mixing, then you would expect this the dashed line, the green dashed line over here. And if you have pseudo-Dirac mixing, then you can see that now you have more energy-dependent peaks and troughs, right, in this picture. Now you can compare this to the data. So if you measure the spectrum very precisely, then you can compare that to this, and then you can do a chi-square, and you can put a constraint on the pseudo-Dirac. That's the idea. But unfortunately, the data is not very precise. We only have like about 25 events from 1987A. But still, in this paper, these people, they went ahead and did a chi-square fit. It's not very good, but still, it turns out that you can rule out a very tiny bit of delta M square with more than 3 sigma significance. So that's shown by this solid curve here. So you can see that if you have delta M square about 10⁻20, okay, maybe 2-3 times 10⁻20 EV square, then that is disfavored by just from this 1987A data. Okay, so this is in a very tiny range, but you can see that to what small extent of delta M square they can go using just the supernova data. And in the future, if let's say we have a supernova detection from 10 kiloparsec in Dune, and then the situation would be much better. And this is a future projection. The current bound from 1987A is shown in blue here. And in the future, if you have either Hyper-K or Dune, then you can probe a much wider range of the delta M square using the same technique if you have a more precise measurement of the energy spectrum. Okay. Any questions so far?
Yeah, could I just break in on that one? So these results that you just mentioned, the exclusion appears to be completely driven by the IMB result.
Right. Yes.
So if you
Oh God.
if you look at Kamiokande or even together with Baksan, there's sort of no problem or essentially no discrimination. So do you understand what's going on here?
Right. Yeah. So I don't exactly remember the energy ranges each of these experiments detected, but it has to go back to this plot on the left. So you see that the deviation from the standard line, that is more if you are sitting at one of these either peaks or one of these troughs over here. And this happens, the deviation is more towards higher energies. So I believe IMB detected the higher energy part of the 1987 spectrum, whereas the Baksan and Kamiokande, they were at the lower energy end. That's why the deviation here is not more, so you don't have much discrimination power. I believe that's the reason.
Yeah, it would be interesting to see the assumptions that go into this plot.
Right.
Given the very small number of events observed, and the fact that I struggle to believe that there was any energy precision in the measurements, it's a little unclear to me how there can be such an exclusion. But
yeah, I totally agree with you. Yeah, in fact, yeah, I'm this. Yeah, as I said, this is not my paper, but this is
if
from
it were right, it would be a different. If it were just a pure rate point, it would be a different matter. But this appears to be rather energy specific, and
right. Yes.
That is ringing alarm bells.
I totally agree with you. Yeah, I mean, this we should not take like too seriously. I mean, yeah, I don't exactly know the details of how they do this fit, but from what I understand from my collaborator, they just simply fit to this energy. I mean, to do this and this. Yeah, but I don't know exactly how good is the quality of the data, and can we really trust this kind of chi-square? Yeah, I totally agree with you. That's yeah, but in the future maybe we can do better. That's the hope from this exercise. Okay. Yeah.
Thank you.
Any other questions on this? Okay, so now let's move on to the high energy neutrinos. That's what I'll focus on for the rest of my talk. So just to review, there are two different ways you can produce the astrophysical or high energy neutrinos. One is through the PP interactions. So this can happen, for example, if you have very high energy cosmic ray hitting one of the protons in some hydronuclear process in starburst galaxies or galaxy clusters and so on. You produce pions, and then the pions will decay to muons and muon neutrinos. Then muons will further decay to electrons and muon and electron neutrinos, and that's how you get 2 muon neutrinos versus 1 electron neutrino. That's the standard 1:2:0 flavor composition that you have. You can also do the same thing with a photon. So photon hits a proton, again you produce pions, and the pions goes to muons and muon goes to neutrinos, and so that's how you produce the neutrino flux. But the main question is that how do you detect these neutrinos? It turns out the flux is extremely small. So this is shown on the right side over here, compared to, for example, supernova neutrino, where the flux is many orders of magnitude higher. So you need really big detectors in order to see this flux. And people have built these detectors like in either IceCube or KM3 network, which are now currently running the biggest detectors for this kind of energies. And so I'll focus on the IceCube because that's what gave us the most of the events so far. So how do you detect the neutrino signals at IceCube? Well, we know that in the standard model, the neutrinos have two types of interactions, either charge current by a W exchange or a neutral current by a Z exchange. And as I mentioned, the flavor composition at the source is 1:2:0 for E versus mu versus tau. And then you can use the vacuum oscillations because they traverse mostly vacuum before they reach us. And so then the flux becomes 1:1:1, just by using the standard PMNS matrix, you can show that. So this is what you would expect for the astrophysical neutrinos, 1:1:1 typically, right? So now how do you detect these fluxes? Well, if you have either a charge current electromagnetic shower or in neutral current shower, then that would give you a localized flux that will give a localized event deposition in the detector. Because the electrons and the hadrons they lose the energy very rapidly, so you just so you don't see much spread in the distance. Whereas if you have a muon, these muons are very high energy, like we're talking about TeV events here, TeV to PeV events, right? So then the neutrino hits the detector and it produces a muon. The muon just flies through the detector, and then you get a nice track like event, which is shown over here. And these are real events from IceCube. If you have a tau, then you can have something even more dramatic. You can first have the hadronic interaction, produce one blob, 1 shower, and then the tau it travels some distance, and then it decays further, and then you have another shower here. So you have like a double bang signature. But this is statistics limited because this only happens above 100 TeV, and the data points they have for beyond 100 TeV is small. So we are not going to consider this for our analysis. Now, another type of event that you can have is what is known as a through-going sample. So here the neutrino, it does not hit inside it does not produce the charged particle inside the detector, rather it produces outside. Now, the outside volume that you have available to you is much larger compared to the inside volume. So the statistics on this through-going sample is really huge. So the idea is the neutrino comes in through the Earth, and then it interacts with the rock outside the detector, produces a muon. The muon just goes through the detector, so it's called through-going. And this is, by definition, it's a track-only event. There's no shower here. And there's huge statistics on this, because basically anything that's coming from the northern hemisphere for IceCube, they're going to have, they could have this kind of sample, right? Now, the good thing with the tracks is that they have excellent angular resolution, because you can see the track very well. So you can pinpoint to the direction in the sky from where the neutrino came in. But the problem is that it doesn't have good energy resolution. That's because the muon that goes through, it does not deposit all the energy in the detector. It only deposits part of the energy. So you have to use some kind of reconstruction algorithm in order to find the true energy of the neutrino. So the resolution at the moment IceCube has about 30%. Okay, I'll come back to this point later because this is important for the constraints that we get. On the other hand, for the showers, they have good energy resolution. In fact, about 95% to 100% energy resolution, because the resolution is like about 1% in terms of the energy, but they do not have good angular resolution. It's about 5% to 10%. Because these events are localized like in a blob, so you cannot really pinpoint to any particular direction in the sky. So ideally you have to have a combination of the tracks and showers in order to reconstruct all the events, or to reconstruct the source location. But at the moment, IceCube only uses the tracks to identify the astrophysical source. Okay, so we are going to just use the track sample for the source identification. And the best example that we have is this particular source called NGC 1068, or the M77 galaxy. Excuse me. So on the left, you can see here the source identification done with the neutrinos, just the mu sample, which is shown by the white lines here, and then the other methods, the optical mostly methods to detect the source, which is shown here. So there's a very nice agreement between these two samples, and this is the example of the multi-messenger detection of the neutrino source at IceCube. And the key point here is to have this good angular resolution, which is shown on the right side plot here. This is the square degrees in the sky. So you can see that if you go to higher, angles, then higher angular sizes, then the data is consistent with the background. But now if you put angular cut of about 1 degree, then you can see this nice peak that's coming mostly from the signal and background remains flat. It's mostly atmospheric background remains flat. So to have good angular resolution to detect the source is really crucial. And this is what was used in the IceCube data, and they got so they have more than 5 sigma significance now. With more than 5 sigma confidence, they can tell that the neutrinos they detect, about 80 of the neutrino events, they are coming from this particular source, NGC1068. Okay. So once we have this information, we can use that to test this the hypothesis that neutrinos can be pseudo-Dirac. So that's the idea of our work, and it's very simple to understand. It essentially boils down to this oscillation effect, and as I mentioned to you earlier, the oscillation length. So the quantity to consider is delta m square L over E, right? So if this quantity is of order 1, then we have oscillation effect. Now, once you know the source location, in this particular case NGC1068, then you know the distance from the Earth. That's just the redshift distance, and then so that basically fixes your L here. And then for a given energy which we measure in the detector, we are sensitive to some values of delta m square. Okay, and it turns out for the length scale, for the distance that we have about 15 megaparsec, and the energy scale that we have about TeV, we are sensitive to delta m square values, which are of order 10 to minus 15 to minus 20 EV square. And that is really proving the pseudo-Dirac nature of the neutrinos, right? So that's another probe of the pseudo-Diracness. So that's the idea. So if the neutrinos are pseudo-Dirac with this particular mass square splitting, then the neutrinos emitted from the source, they will be active neutrinos. And then by the time they reach to the Earth, they just oscillate into half sterile, intersterile component, right? So half of the flux will be lost to us. And so you'll get a deficit in the flux of the neutrinos. And so using this deficit, if you don't see this deficit, then you can put a constraint on the mass square splitting. And if you see a deficit, then of course, then you can make a statistically significant statement that neutrinos could be pseudo-Dirac. So that's the idea. Now you can ask this if some astrophysical uncertainty, for example, right? Because we don't know what is the flux at the source. We don't know the normalization of the flux, and we don't know the spectral index so well. We have some, there are some indications from the IceCube data, but there are large uncertainties on that. So can any of these effects mimic the pseudo-Dirac effect that we're talking about? Well, it could be true if you have a single source, but now if you have multiple sources, which is shown in this picture here, if you have a second source, you have different baseline length, and it is sensitive to different delta m square value. So if you have multiple sources, you can combine this and you can draw a combined sensitivity to delta m square, which is very difficult to be mimicked by any astrophysical uncertainty. So now if you increase the number of sources, then the chances that any astrophysical uncertainty can mimic this particular, if the flux deficit effect, that will be very, very small. So the more sources we have, with more certainty, we can tell that we can really probe this delta m square. Okay, so that's the idea. And I can explain all of this in equations. So the oscillation probability you can calculate using this quantity here. Again, the delta m square L over E comes into picture here, where L effective is, that's basically the total, including the redshift and everything. That's the effective length, baseline length. And E nu is the energy of the neutrino that we observe. So here is a plot of this effect. This is the x-axis, the energy, and the y-axis is the oscillation probability. So we plot for different flavors in nu mu. So we can have the survival probability, nu mu to nu mu, which is the orange line. Excuse me. And then you can have the appearance probabilities of nu mu to nu e or nu tau. And then you can also have this, if you have pseudo-Dirac, then you have this possibility of having nu mu going to sterile. And that will be invisible to us, right? So that's how we get the deficit of the event. So as you can see from this plot, so I have chosen a particular delta m square over here. And you can see that there are energy values where this oscillation from active to sterile becomes maximal, right? So you get probability of active to sterile oscillation maximal. So if you are sitting at one of these points, then you see the deficit in your energy spectrum, okay? And now, so if you have the data for the energy spectrum, we can use that and we can put constraints on these delta m square values, okay? And you can calculate what's the typical oscillation length for this particular for energy of about 1 TeV. And the oscillation length turns out to be about 6 megaparsec, which is roughly the size of the distance to the source. And so that will be sensitive to a particular value of the delta m squared, which is shown over here. Okay. So here is a plot for the spectrum. You can see this effect very clearly. The black line here is the standard fit to the IceCube data for 3 different sources. First, I saw the NGC1068 that has the highest significance, but there are 2 other sources which are more than 3 sigma significance. So we also include those in the analysis. Then the field regions, they are the predictions you get for a particular value of the delta m squared non-zero. Okay. And you can clearly see that there is a deficit now in each of these energy bins. If you assume that the spectral index is the same as the standard fit, then you can clearly see the deficit in almost all the energy bins over here, right? And now we can do a simple chi-square, and you can find what is the what's the limit that you can set on the delta m square value. So as I said, if you have more than one source, then you can do this more accurately, and then you can get rid of all the astrophysical uncertainties by having multiple sources in combination. And in fact, you can even let the spectral index here go floating. You don't have to use the same spectral index. For example, if you have pseudo-Dirac scenario, you can mimic it by using a different spectral index, for example. And this is what you'll get. Instead of this dark solid, you'll get the light solid, but still you get the deficit. So you cannot get rid of the deficit even if you have the most conservative scenario with everything floating, the spectral index floating. You can also let the normalization of the flux floating. So no matter what you do, you still have the deficit if you have a sterile, okay, for the right value of the delta m squared. So now you can.
I've got a question here. So do you have to assume that all of the neutrinos are coming from PP uniformly, or what happens if some sources are PP and some are P gamma?
Yeah, so here it does not really matter for us, since the only thing that we're looking at is the muon. So as long as you get muon neutrinos from the source, then we are fine, right? And I'm taking these particular sources because we know the distance to these sources now. So that's all the information we need. We need the distance to the source that fixes the baseline length for us. And then all we require is that they should have muon neutrinos, so that we get these track effects, so that we can pinpoint to the source, right? So that's all we need.
Okay.
Whether it's P versus P gamma, it doesn't really matter for us at this stage.
Okay, thank you.
Right. Okay, good. So now a little bit more about the flux uncertainty. So actually, IceCube has done 3 different types of fits. They have a single power law, which is what you see over here for the black line. And then they also have done the single power law with a cutoff, and then a log parabola type of fit. So we can we take all of that into account. You can just consider this. These are all kind of the different floating parameters you can put in the fit, and still you can get some meaningful constraint. Okay, so that's what I show in this plot. Now, so these are real constraints, okay, that we get from IceCube data, just from the current IceCube observation. Now, the significance is not so good. It's like only 2 sigma significance, but this is like a proof of principle that this method works. And also you see that you are sensitive to different mass splitting range depending on the location of the source. So for example, this NGC1068, that is relatively close by. It's only 14.4 megaparsecs from us. And that means that you are sensitive to a bit larger values of delta m squared, whereas the other sources, they are far away from us. So they are more sensitive to smaller values of delta m squared. And it also depends on the energy spectrum for this particular, the third source here, the energy was a bit higher. So then it can push back toward the higher end of the delta m square and so on. But yeah, so roughly speaking, if you have sources close by, that will be proving a larger value of delta m square. If your source, which is far away, that's going to prove smaller values of delta m square. Okay. So this is what we get for the current IceCube data. And then we can also make some predictions for the future. So in fact, in the IceCube paper, they have also many other sources listed. which are identified with less significance. For instance, they have all these sources which are identified with roughly 1 sigma significance. So that's why I did not include them in the first plot that I showed. But in the future, let's hope that some of these sources can be identified with more than 3 sigma significance. So in that case, we can include all of them in the picture. For example, if you have Gen 2, then you can do this, you can have more exposure, so you can have more statistics, and in principle, more sources could be identified with 3 sigma significance or higher. So once you include all of these, so you have like 10 sources, I believe. So if you include all of that, then you can go up to maybe more than 5 sigma significance in the future. Okay, so that's shown in this plot. And you can also cover a larger range of the delta M square, again, depending on the distance. So here, they are coming from all over the place. Distance small, distance large. So you can include all of that together, and you get a wide range of the delta M squared cover here. And just to remind you, in this plot, this is the supernova constraint that I mentioned before from 1987A. This is like a very narrow window. This is a tiny bar here, around 10 to minus 20, 2 times minus 20 EV square. But from IceCube, you get a much wider range of delta M square constraint. Okay. Let me see. Yeah. So one thing I want to mention here is a technical point about the effect of energy resolution. I mentioned that the energy resolution of the track sample is not very good. It's roughly about 30% at the moment. So with 30% track sample, this is what the sensitivity that we get, about 2 sigma here, the second line. And if you had a better energy resolution, then you can even have better constraints. Okay. So for example, if you had 10%, which is kind of a dream, I don't know if it's realistic, but if we had that, then you can see that with the current IceCube sample, you can already go to about 4 sigma or higher sensitivity. So the question is it possible to have this kind of good energy resolution for the tracks? Well, the answer is maybe. Again, I don't know. Since I'm not an experimentalist, I cannot tell how long it would take or whether at all you can possibly do this. But there is certainly a lot of room for improvement with better technology for these digital optical modules. They, in principle, could improve the resolution, and that's something that I hear from the IceCube colleagues that this is something they're actively working on. So in principle, this can be done. And then including showers to the sample will also improve the situation, because remember that the energy resolution for the showers is very good. It's at the level of 5% at the moment, but the only thing is the angular resolution is not good. So if somehow the angular resolution can be better for the showers, then we can add those to the sample, and then we can get even better precision. And this is apparently possible with the water-based detectors, because I think from the optical properties of the neutrino propagation in water versus ice, it turns out that the water has better angular resolution for the showers. And there are 2 detectors that are currently being built. One is this KM3 network in the Mediterranean, and one is this P1 in Pacific Ocean of the Vancouver Island. So if you include all of these, then in the next maybe 10 years or so, it's possible to imagine that we can have showers also giving us a good reconstruction of the source identification. So then situation can be improved. So I would conclude this part of the talk by just mentioning this this vision of having a planetary neutrino telescope. This is a slide from Matthias Huber from GUM, where he talks about this network of these different neutrino telescopes. The IceCube is right down here, and right now we have this KM3 network under construction in the Mediterranean. This P1 is over here, and then there is one in Russia, Lake Baikal. And that's also the upgrade of that is also under construction. So you can use all of this and make this planetary neutrino network and add to the statistics. So in the future, we hope that this can be used to improve the sensitivity to the pseudo-Dirac scenario. Okay, so I don't know how much time I have for the.
So it's 5 to 11, so you can still take a little bit more time if you want.
Okay, so maybe I'll just take 5 minutes, if that's okay, to talk about the second part, where I'll so this is some work still in progress. We hope to finish it by next month. But the idea is that so far we talked about only maximal mixing between active and sterile, right? Now, if you have non-maximal mixing, for instance, if the mixing angle is very small between active and sterile, then the methods that I discussed for the ice cube, it doesn't really work, because if you have very small mixing, then all the flux and everything, the probability that it will go to the sterile is very small. So then you cannot really use them to probe this pseudo-Dirac scenario. So is there any other probe? Well, it turns out that you can do something else over here. So this plot shows the current constraints on the active sterile mixing versus the delta M square, the mass splitting between them. So we typically talk about larger mass square splittings. When you talk about the EV scale sterile neutrinos and so on, there the maximal mixing is anyway excluded. But if you go down in the delta M square, still it turns out that the solar neutrino data is so precise that it excludes the active sterile mixing all the way to about -11 EV square. Okay, so if you have 100% mixing, if you have maximal mixing here. But now if you go to the smaller mixings, then there's a lot of white space, as you can see here. So in principle, you can have a scenario where you have a delta M square which is larger, not 10 to -11 EV square, but maybe around -3, 4 EV square, which is more interesting. But you can also have a small mass splitting, and you can allow it. So in this plot, you might notice there are two boxes here, which one shows Arcadi, one shows edges. And this, in fact, is a possibility that you can explain some anomalies in cosmology using this pseudo-Dirac neutrino with a little bit larger mass scale splitting in this mass range. And the idea is that you can have the relic neutrinos with active neutrino decay to a sterile component and a photon, which is possible if you have mass scale splitting of this value. Then it turns out the photon frequency, the photon energy, it turns out to be exactly in the range of this Arcade radio band or this edges 21 centimeter line. So you can, in principle, explain these anomalies if you have this decay of an active neutrino going to sterile. I don't have much time to explain the details of what the anomalies are, but just in one line, Arcade is a balloon experiment that was looking for the excess radio background, extragalactic radio background, and this is what they found. The experiment was in 2009. Well, the experiment was probably before, but they published the paper in 2009. So this is a power law fit to the data, and they have some excess in this particular frequency range between about 3 to 10 gigahertz frequency. Okay, so they have some excess at antenna temperature, which cannot be explained by a simple power law. So the question is there anything, any BSM explanation which can explain this? And one of the ideas is that, yeah, you can have a relic neutrino decay. So if you have an active sterile mass splitting of this particular order, 10 to -3 to -4 EV square, then you can actually find that it provides a very good fit to this excess radio background. This is shown in this plot here. So depending on where you use a delta M, just the mass splitting, not the square, where is the delta M? Depending on that, you can fit either, there are 6 points which have the excess, well, there are actually 4 points which have excess and 2 points which are slightly away from the power law. And depending on where is your delta M, you can fit one or more of these points. Then you can do a chi-square, and then you can find what is the allowed region which explains this excess while being consistent with all the other constraints. And that is shown in this plot here. This is the region which explains the Arcade excess, and that's consistent with all the other lab constraints that we have. And the lifetime is incredibly long here. So the lifetime of the decay is like 10 to 21 seconds, certainly is larger than the age of the universe. So very slow decay. But this lifetime is needed in order to get the okay. So in order for this neutrino to explain this particular frequency band, okay, and this particular mass value over here. And then I also saw here the region that is preferred by the edges 21 centimeter line, an anomaly. So this, just to remind you, edges is an experiment in Australia, which looked for this absorption line in the 21 centimeter hydrogen from the dark edges around G equal to 15 to G equal to 20. And they found an absorption which is 2 times stronger than what you would expect from standard lambda CDM. And one of the possibilities is to either decrease the gas temperature at that redshift, or to increase or to increase the inject some extra radiation, which will increase the background temperature. And if you have this relic neutrino decay, then you can inject more energy. You can inject some photons into the background, and that heats up the background, and that is one possible way to explain this anomaly. So it turns out that these two regions actually don't overlap exactly, but they're pretty close to each other. And there is some region here where the overlap is a very, very tiny region where the overlap, but it's not the best fit point. So yeah, so I mean, obviously, I won't take this very seriously, this overlap region, but yeah, we need more data to confirm whether any of these anomalies is actually true or not. But if this is true, if either of them survive, then this is one of the possibilities that one can use to explain this. If both of them survive, then probably this model is not right. We need something else. Okay, so I think with that, let me stop here. I'll just conclude. So the nature of the neutrino mass is an experimental question. And here we discussed a new experimental probe using the astrophysical baselines. And this is made possible by the recent observation from IceCube, which identified the source of these high-energy neutrinos. And using the current data, we can already probe the delta M square values in this mass range, 10⁻⁻21 to -16 eV square. And if you have in the future more statistics, then we can improve the significance to maybe more than 5 sigma. And finally, I talked about the non-maximal mixing case, which can in principle explain the excess radio background and the 21 centimeter anomaly using the pseudo-Dirac neutrinos. So I'll stop there. Thank you.
Yeah, thank you very much, Bhupal, for a very interesting talk. So we already had some questions, but we have time for more questions. Who would like to go first? Or maybe let me start off. So if you go back there, those 2 slides or 3 slides when you talked about that excess. So yeah, you could technically you could turn it around, right, and just use it as a probe for those neutrinos, for the pseudo-Dirac neutrinos, and also constrain that scenario, right? So even if you cannot explain the excess, also even if there is no excess, you can use it as a constraint.
So you mean that, okay, so if you have a pseudo-Dirac, then if it goes beyond this power law, then that is constrained by the data. Is that
yes, yeah.
Well, it's possible if you go to such lower frequencies, but here you see this log scale, right? So the contribution from the neutrino decay is really small. So you can see that here. So it's like at the level of 100 millikelvin. And then this power law, it goes way up there. So if you're looking at the smaller frequencies, then you need to have a much larger signal from this relic neutrino decay in order to compete with the power law. But this is relevant in this part of the frequency range simply because the power law is falling down very rapidly. And so in this high frequency range, you have more sensitivity. But unfortunately, we don't have data from Arcade beyond this 10 gigahertz. Apparently, they had like 8 different radiometers, but some of them malfunctioned, and they could not get the data beyond this. And then they have one data point over here. It's about more than 100. This is not from Arcade. I think this is from Virus, and that is completely consistent with the fit, the power law fit. So there's no excess over there. So yeah, if you have, in principle, you can use those higher frequency data points to put a constraint on the decay scenario. Yeah, this is something that we did not really look at. We're more kind of intrigued at this stage by this excess, but yeah, that's a good point. We can use the higher data from other experiments, and we can put a constraint on the relic. Yes.
Yeah. Thanks. Roland has a question. Another question.
Sorry, I'm in a noisy spot, so I apologize for the ambient noise. So IceCube is now saying that it detects the galactic plane in high energy neutrinos. So I wonder whether it's obviously probing a different baseline, but have you thought about incorporating that into your results?
Yeah, so let me go back to this plot over here. Right. Yeah, so here I mentioned about the distance scale here for the high energy neutrinos, but I was mostly thinking about extragalactic sources. But yeah, yes, you're right. Now IceCube has detected the galactic plane, so we can extend this down to few kiloparsecs. which will be where 16 is 1 parsec, so maybe around 19 or 20. So it will be extended up to this. Yeah, so we can in principle probe the gap between the solar constraint, which is 10 to the minus 11, and right now the ice cube constraint that we have is minus 16. So we can really probe this gap in between that using the galactic neutrinos. Yes, that's correct.
Okay. Thanks.
Can you go back to those? You showed those different models for the fluxes for the
Right.
from those different astrophysical.
Yes, so ice cube has these 3 different fluxes they consider.
Yeah.
Excuse me.
So in your fit you used all 3 of them, or you used?
Yes. Yeah. So we basically let the we basically agnostic about the exact shape of the so yeah, we consider all 3 of them. We just kept it as a floating parameter, and that's already included in our fit. So yeah, so that's why you see this 2 sigma here. If you just take one of them, and initially what we did, we just a single power law, then we're able to get like up to 4 sigma. But that's of course probably not that's very optimistic, because we don't know the exact power law, and from ice cube data it looks like all 3 of them fit very good. At the moment they cannot distinguish between any of these 3 different fits. So I think so to be honest, we have to include all of them and we just let it float and then find what's the chi-square. Yeah.
Okay, and for each of the sources you do it independently, is that right?
For each
or
of
is
them,
it?
yes, exactly. Yeah, for each of them we do independently, and this, but we get some this gamma. So the ice cube has given the best fit for these gammas. There's some error bar, I did not show it here, but yeah, so include all of that. But yeah, when we only do the single power law, and then is the single power law with cutoff, we similarly do. I think ice cube has some information on these other fits. They have given some error bars there as well. So we use all of that, yeah, and then then do it individually for each of the sources that we analyze. Yes.
Okay. So but what's actually the most constraining factor? Is it the energy resolution or the uncertainty from the sources?
So actually the uncertainty does not really matter so much if you have multiple sources, because the effect is very difficult to mimic. So I think I showed it in one of the sorry, I'm going the wrong direction here. So this is what we have. Just if you take single power law, this is what you'll get, right? So, and you see the deficit is very clear in multiple energy bins. Now if you do the floating spectral index, then this is what you get. Now the deficit is only like 1 bin, but then there's an enhancement in another bin. So you can still use this data. You can still use it to constrain it. So you don't lose that discriminatory power so much, especially if you combine with multiple sources, because in one case you get an enhancement here, but in the other case you do not get it. And so you can use that in order to, so you can use multiple sources to reduce the astrophysical uncertainty. I think what is mostly limiting factor at the moment is the energy resolution. Yeah, and that's the effect that is showed over here. So just the energy resolution improvement can give us better sensitivity here.
Okay. And you couldn't include the other events, the basically which are not track-like, because they're just because of you cannot associate them to the source.
Exactly, because the angular resolution is not so good. They're like 5 square degrees in the sky, and there can be many sources there. We have no idea where the source location is, so we cannot use them at the moment. Yes.
Yeah. Thanks. That's Roland.
I wonder whether you can do the analysis with the isotropic flux with some model for the neutrino flux that you get from the cosmologically distributed population of sources.
Yeah, if you do isotropic, then we don't know the location of the source, right?
No, I know, but if you have a model, you have some expectation for what the mean distance is, or some expectation for how what the expectation distance is for the expectation is for the distance to the source.
Right, but that will have a larger uncertainty, I believe. And here the distance is very crucial for us, because the distance sets the baseline length. So if you change this distance, so here I did not put error bars, it's there in the paper, but error bars are pretty small here. I mean, the distance is very well measured, because I mean these sources have been looked at in many different wavelengths, mostly optically, so the source distance very well. So that fixes our baseline length, and that's the starting point, right? Then we know to which delta m square we're sensitive to for a given baseline length. Now, if you change that, for example, if you have like a diffuse emission, like you're saying, in that case, we don't really know the location of the source, and it can take a mean distance, but then it has larger uncertainty, and that will feed into this delta m square. So that will be another uncertainty that we have to include in the analysis. I don't know on top of my head whether this effect is large or small, I mean, compared to the energy resolution effect, but this is, yeah, I mean, we can check it. Yeah, but I think here, yeah, the distance is really, yeah, here the distance doesn't have much uncertainty, and so that's why it does not really contribute to the uncertainty that we have at the end, and in terms of the likelihood.
Yeah, well, it might be good to talk offline, because I have a model for how those neutrino sources distribute cosmologically, which is related to the which we can, with this model we can reproduce the isotropic gamma ray spectrum. So at lower at Fermi band energies. Anyway, I'd be interested to talk to you more about that.
Yeah, I'll be happy to discuss further. Yeah.
Thanks.
Yeah, Bruce.
For what it's worth, I've skimmed the relevant part of that paper discussing the supernova 1987A
Right.
neutrinos, and I don't believe a word of it.
Okay. Okay. Yeah, I have nothing. Nothing at stake here. But yeah,
the number of events is small, as you know. They don't appear to have any systematic treatment of their own that they use in the analysis, and as far as I can see, it's piggybacked off some previous standard joint analyses that argue that sort of systematics in the IMB efficiency don't matter, or don't matter that much. Now, I can believe that for a joint fit that just tries to find out what was the intrinsic luminosity and what was the neutrino temperature of 1987A. If you're trying to do that across the three experiments, then I can imagine that systematics and IMB don't bother you that much. But if you're trying to play the three experiments off against each other and decide, is it a standard or a non-standard spectrum, then I think the idea that you can do some naive fit of a shape and it doesn't include systematics is just bonkers. So
yeah, I can believe. Yeah, I tend to agree with you. Yes.
Rant over, bearing in mind that I've just skimmed the key plots, but it's if you look at the money plot in the relevant paper, it's eyebrow raising.
Yeah, that's quite possible that they did not take into account the systematics properly. Yeah.
Yeah.
Okay. As I say, rant over.
Yeah. Good. Can I ask one last question? I see that we are, of course, over the time. So you mentioned briefly in passing in the beginning that the bound for kind of from BBN or from any effective for Dirac neutrinos.
Right.
But what's the bound for pseudo-Dirac neutrinos? Do you have there? You should also get a bound, or for pseudo-Dirac neutrinos.
Yeah, so
it's very similar.
It depends on what's the mixing. So for this is true for maximal mixing. So if you're considering maximal mixing, then this is this is the bound for the pseudo-Dirac basically also, right?
Okay. Okay. Yes.
Because for the Dirac
maximum mixing.
Yeah, right. Because for Dirac, the delta m square is simply 0, which is consistent with this bound. Right? Yeah.
Yeah. Okay. Good. Yeah. Sorry, I missed that. You mentioned it.
I think you maybe referring to the delta ineffective part.
Yeah, the delta ineffective. That's what I was.
Ineffective, right?
wondering.
Yeah. So this is So I think Dirac will predict this to be 0.14, which is right now consistent with the Planck data. But in the future, if you can measure delta effective more precisely, then in principle, I think this is testable at CMBS4, where they claim that they can go down to like 0.1 or even below that for delta effective.
Yeah, and the same should basically apply for pseudo-Dirac neutrinos, right?
Exactly. This will
Because-
but I guess the point is that just if you observe something here, then we don't know whether it's Dirac or pseudo-Dirac.
Oh yeah, that's for sure.
But
That's
then
for sure.
we need to look for the oscillation effect, and that's what we are trying to do here, right?
But if we don't observe anything, then we can constrain it, of course. Then you
Right.
could
That's true.
constrain additional right-handed degrees of freedom.
Constraint of the pseudo-Dirac, that's correct.
Yeah.
Yes. But it's kind of model dependent because the actual value of delta effective depends on how the sterile is thermalized.
True.
It depends on the interactions. And for example, in this model, they have the right-handed interactions, they have the B-L interactions. If you have just B-L, then the bound will be different and so on. So yeah, that becomes model dependent question then.
True. Exactly. Yeah. So if you would just introduce the right-handed neutrinos and no gauge interactions, then they may not even thermalize. Yeah.
Exactly. So then there is no delta effective bound.
Yeah. Okay. So it's really from those from those gauge interactions actually. Okay, that's good. So I would say let's thank Bhupal again for a very interesting talk, and I'm sure he's happy to answer a few more questions. But